Okay, hello. So today I'm going to be discussing a problem number 81 in chapter 6, which is, of this textbook. I don't know if that's how full chapter 6 is. I believe, like, energy and work or something. I'm not, not exactly sure. But, we're going to be working with this problem and it was very difficult for me, so that's why I'm making this video. So, start off with the givens. We're given 75 kilogram bicycle, 4-degree hill, 10 kilometers per hour, and then they can pump hard to get to 30 kilometers per hour. So, we can see it's using power and speed climbing there. And then the last thing is, friction is proportional to the speed v. So, okay. I'm going to draw a little diagram. What's going on here? So this is a 4-degree hill. And I'm going to just draw a box for our bike. So if we draw a free body diagram of our bike, we can see we have a weight here, our normal force, there's mg cosine and mg sine theta will be pointed down. Okay, and so if you notice, it says it's going down at a steady speed. But when you're accelerating due to gravity, usually you're going to be accelerating, not going at a steady speed. So that means there's another unknown force here. That is the frictional force, they're calling it friction. But it's just a force of all the frictive forces, like air resistance, blah, 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 whatever. So I'm going to add that as BV. So the first step in solving this problem is to solve for BV, or for B specifically, since it says it's a constant. So what I'm going to do is I'm going to set up this diagram thing for where we're going 10 kilometers per hour. And unit conversion, 10 kilometers per hour, you can multiply it by, I think, 5/18. But 10 kilometers per hour will be around 2 point, is it 7? I think it's 7, let me just verify. 10 times. Yep, it is 2.7, actually repeating meters per second. But, basically, so yeah. So, the only forces we really care about here, so obviously you have gravity. I'm gonna just break into its components of cosine mg, and then sine mg. But then we also have this BV pushing up here and our normal force. So it says at a steady speed it's coasting down, so there's no other forces applied by the biker. So what I'm going to do now is I'm going to set up some reference axes. So I'll just say positive here, positive, I'll just put x and y. So I'm going to set up our equations now. So mg sine theta minus bv equals 0. So I'm not going to set up this axis because it doesn't really matter, because we're only really concerned about how we're moving down this hill. So this is 0, of course, because we're going at a steady speed, so the acceleration is nothing. So yeah. And so the velocity here is 2.7 meters per second, so we could very easily solve for b by just doing some quick algebra. So b equals, if we put on the other side, mg sine theta over the velocity. And our velocity and mg sine theta are all givens, or all things that we can calculate. So it's going to be 75 times 9.8, because that's gravity, times sine of 4, again, 4-degree hill, divided by our velocity. This is going to be in meters per second, 2.7 bar. And putting that into a calculator, we get a value of b is equal to 18.457. The units for this, let's see, would be kilogram meter per second squared times seconds per meter. So that would be kilogram seconds. I don't think the units are very important, but anyways, so now that we have this, b, it's constant, so it's going to be like the same for all of them. We're going to see how much power the cyclist can put out. So they're going at 30 kilometers per hour. So I'm going to set up another triangle thing with this cyclist again. So we still have mg cosine, or sine, sorry, mg sine, and there's still a bv, but this time I'm going to say we're going 30 kilometers per hour. 30, that in meters per second, that's roughly 8.3 bar meters per second. So I'm not concerned about other forces. This time, though, we also have another force to counteract this friction, because of course this is proportional to the velocity, and we already calculated what our b is, which is 18, so it wouldn't make sense for the weight pulling it down to stay the same, but then the friction to go and increase without any other force, because then that would mean it's going upwards, but of course we know it's going downwards and not accelerating. So there's another force, which I'll just call FB, which is a force that the biker can exert, basically. And of course, this is just our mass, again, 75 kilograms, and we're heading down in this direction. So what I'm going to do now is I'm again going to set up equations, reference axes plus y plus x. So we have force of biker plus mg sine theta minus bv equals 0. Again, we're going 30 kilometers per hour, but at a constant speed. We're assuming that, given the framing of the question. So to solve for the force of the biker, what we're going to do is we're going to just put this and that on the other side. So bv minus mg sine theta. Of course, we know all of these values because we've just calculated b, so that's 18 point... We said b was 18.457, I'll just say 18.5 times our velocity, which we say is 8.3, repeating, and then minus mg cosine theta, that's 75, not 7.5, times 9.8 times sine of 4. So we have 18.5 times 8.3 repeating, and then we're going to be subtracting 75 times 9.8 times sine of 4, which will give us a force for the biker of 102.89 newtons. So if we look at this problem, it's asking for the power that this person is working at, but we only have the newtons. So we have to define what power actually means. So power is colloquially known as work over time. Of course, work is force times distance, so you can say force times distance over time. And then again, distance over time, if we're going in a straight line downwards, would just be velocity. So you can say this is force times velocity. And look at that. We have a force, and we have a velocity. So what we're going to do now is we're going to calculate the power. So power is equal to 8.3 times 102.89, and we get a value of power of roughly 854 watts. And so now, from this, we have the same power now. So what speed can the cyclist climb the same hill? So this time, I'm going to keep this over here. we're going to draw one final diagram. And we have this time the biker still 75, and they're climbing up this hill at a velocity which we don't know. So, to figure out what's going on here, let's draw another free body diagram. So we have our mass, of course we have n, the cosine portion of mg, and then now mg sine theta is down, but guess what's also pointing downwards? Our force of friction, which I'm going to put as B times V. And this is because we're heading upwards and friction opposes motion, so it's going to be heading downwards. So that means that the force felt over here is going to basically be all the power that this biker is putting in. Power isn't a force directly, but force, or if we divide by velocity, it will be. So what I'm going to do now is I'm going to set up an equation to solve for this power. So we stated that power is equal to force times velocity, and over here. And if power is equal to force times velocity, our force over here we can calculate. So the sum of the forces is equal to, actually not sum of the forces, I'm going to say this is our force, big force. So the force has to be equal because this is going to be going up at a constant speed. It's not going to be accelerating upwards. So the force, I'll set up reference axes first actually. So let's just say it's like that again, plus x plus y. So we have bv plus mg sine theta minus force equals 0. Again, this is a force that the biker is exerting. So bv plus mg sine theta is equal to the force of the biker. And so now that we have this force of the biker, we're going to shove it in there, then we're going to solve for our velocity. So we have power equals bv plus mg sine theta, again, times velocity. So we have our velocity down here. So now all we have to do is sub in our values. So we have a power of 854 watts. So I'm going to go to the next page. 854 equals, we know what B is. B is what we calculated on the first page, which is 18.457. I'm going to just say 18.5. V, mg, and sine are all givens, so that's going to be 75 times 9.8 times sine of 4, and then we just have another v that we're solving for. So now I'm going to distribute these, and we'll get 854 is equal to 18.5 v squared plus, I'm going to just shove this all in a calculator again, so 75 times 9.8 times sine of 4 is going to be equal to 51.27, and this is going to be multiplied by v. So now what I'm going to do is I'm going to take this value, shove it over to the other side to get a quadratic looking thing, 18.5 v squared plus 51.27 v minus 854. Now all we need to do is solve for velocity using the quadratic formula. I'm going to put it into my graphing calculator. 18.5, 51.27, and negative 854. And we get two values of velocity. I'm going to pick the positive one because we're not going to be going in a negative direction. So 5.548. And conveniently, the other value of velocity that we're going to get is actually the original velocity here, which is saying how fast it would go if it was using the same power to go down the hill. This time we're just looking at the power it takes to go up the hill, and this is going to be in meters per second. And if you want it like the prompt, what we can do is we can just take that value, multiply it by 18 and divide it by 5, and then we get a value of 20, which is 20 kilometers per hour. So the most important part of this problem is to remember that power and force are two different things. Because if you solve for this equation using only force and you ignore the power, you're going to get a different value because that's not taking into account the speed at which this person is going when they're exerting that much force, which is the whole point of this problem. So it's very crucial that you make sure to include that value. But otherwise, that's how you complete this problem. Thank you. And yeah.